Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to focus on solid state. What is solid state? In this content, I will discuss definite volume and shape, which is the characteristic of solid state, regular order of arrangement of particles, strong intermolecular forces, and low kinetic energy. So, classification of solid. Solid can be classified as crystalline or amorphous on the basis of arrangement of constituent atoms or molecules. What is crystalline solid? A crystalline solid is composed of one or more crystals. Each crystal has a well-defined, ordered structure in 3 dimensions. They have sharp melting point. Examples include sodium chloride and sucrose. An amorphous solid has a disordered structure. It lacks the well-defined arrangement of basic unit found in a crystal. They melt over a wide range of temperature. Glass is an example of amorphous solid. So, you can see here crystalline and amorphous crystals differences arrangement of atom. Now, classification of solid. Solid can be classified into 4 types based on nature of bonding: molecular, covalent, metallic, and ionic. In molecular, van der Waals forces; in covalent, covalent bond; in metallic, metallic bond; in ionic, ionic bond. Now, molecular solid. A molecular solid is a solid that consists of atoms or molecules held together by weak intermolecular forces. Many solids are of this type: soft, low melting point, volatile, electrical insulators, poor thermal fusion. For example, solid neon melting point of minus 248 degrees Celsius, solid carbon dioxide dry ice, solid water ice, iodine sugar. In nonpolar molecules, the intermolecular forces are only weak van der Waals forces. Polar molecules have dipoles and so have slightly stronger attractions between them, meaning that the melting point of a polar molecular solid is little higher because more energy is needed to overcome the slightly stronger forces. Molecular solid. Examples: positions of an iodine molecules you can see in this picture. Now, forces of attraction between the particles weaken by increasing the temperature. Liquid iodine. Forces of attraction between the particles broken by further raising the temperature. Gaseous iodine. So, conversion from solid iodine at room temperature to liquid iodine, and finally gaseous iodine. Now, molecular solid. Ice solid form of water. Each oxygen atom inside the ice hexagon lattice is surrounded by 4 other oxygen atoms in a tetrahedral arrangement. The distance between oxygen is approximately 2.75 angstroms. The hydrogen atom in ice are arranged following the following manner. You can see in this picture oxygen big one and hydrogen small. 2 protons are close, about 0.98 angstrom to each oxygen atom, much like in a free water molecules. Each water molecule is oriented so that the 2 protons point toward 2 adjacent oxygen atoms. There is only 1 proton between 2 adjacent oxygen atoms. Under ordinary condition, any of the large number of possible configuration is equally probable. Now, molecular solid, the covalent bond inside the molecules are very strong. The molecule don't break apart easily. However, the forces attracting neighboring molecules to each other are very weak. It is therefore very easy to separate molecules from one another. Examples: ammonia. You see the strong covalent bond inside the molecule. Very weak attraction between the molecules. When a molecular solid melt, it is the forces between the molecules which are broken. Very little energy is needed to make this happen. So molecular solid have low melting point. Now metallic solid. A metallic solid is a solid that consists of positive metals ion held together by a surrounded sea of electrons, metallic bond. In this kind of bonding, positively charged metal ion form the lattice which is submerged in the sea of electrons, or the metal ion occupy a fixed position in the lattice structure and they are surrounded by delocalized electrons. Therefore, the intermolecular forces in metals must be rather strong, very soft to very hard, low to high melting point, good conductors of electricity and heat. Metallic luster, malleable and ductile, moderate heat of fusions. These are the properties. And examples: iron, copper, and silver. So you can see how sea of electrons in this pictorial diagram. Now metallic solid. The lattice is held by a strong electrostatic attraction between the delocalized electron and metallic cations, known as metallic bond. The strength of metallic bond varies, and so consequently the melting point and boiling point of different metals varies. Malleable and ductile due to non-directional metallic bonds. Good conductors of heat and electricity due to high density and mobile electrons. High melting and boiling point due to a strong metallic bond. Stress applied, you can see delocalized valence electrons and metallic cations, and attraction between the cations and delocalized electrons. Illustration of the malleability and ductility of metal. Now, ionic solid. An ionic solid is a solid that consists of cations in an ion, held together by electrostatic attraction of the opposite charge, ionic bond. Brittle, high melting point, good conductors in the aqueous solution or fused state, high heat of fusion. Salt like sodium chloride, potassium nitrate, lithium fluoride, barium sulfate. Sodium chloride, you can see this is the crystal structure of sodium chloride. And you can see here how positive and negative charge attach to it. Now, ionic solid. So, properties of ionic solid. Do not conduct electricity, no free ion or electrons, except when molten or aqueous, as ions are free to move. High melting point and boiling point because of very strong electrostatic attraction between the cation and anion. Soluble in polar solvent. You can see here hydrated sodium and chloride ion. Notice the orientation of the water molecules around each other. You can see this is the chloride and around us hydrated anions, sodium and water molecules. Now, properties: high melting point and boiling point, hard but brittle, stress applied, then repulsion of the like charges, fractures structure. Structure is deformed and break apart. The giant ionic structure fracture when stress is applied. Now, covalent solid. A covalent network solid is a solid that consists of atoms held together in a large network or chain by covalent bonds. Very hard, high melting point, poor conductors of heat and electricity, high heat of fusion. Examples include carbon. It is in its forms as diamond or graphite, asbestos, and silicon carbide. Three types: linear chains, 2D layers, and 3D covalent network. So covalent solid. Linear chains are infinitely longer linear chain held together by van der Waals. Properties of the covalent solid: low melting point, but longer chains have higher melting point than shorter one. Do not conduct electricity, soft and flexible. For example, polythene, rubber, plastic. Ethylene is the monomer unit here. Then polymerization by opening of the double bond. This is polythene chain, carbon, hydrogen. You can see in this picture. 2D layer held together by weak van der Waals forces. Graphite is made of a layer of covalently bonded carbon atom. The layers are held together by weak van der Waals forces and have delocalized electrons between them. This is very unusual, and graphite is the only non-metal to conduct electricity. You can see the graphite, a strong covalent bond between the carbon atoms in each layer. Weaker forces hold the layer together. 3D covalent network solid are made of atoms held together by a strong covalent bond. Diamond and silicon dioxide are two examples of covalent network solid. Diamond is the strongest substance known to man. Covalent network solid have high melting point, a strong covalent bond, hold atom in place, do not conduct electricity, all electrons held in covalent bond, very hard, strong, insoluble in any solvent. So you can see here diamond, you can see here silicon dioxide. So this is the table for the comparisons: covalent, shared electrons, ionic, electrical attractions, metallic, electron-C, molecules, van der Waals forces. Examples: diamond for covalent, sodium chloride for ionic, copper for metallic, and ice for molecular solid. Then properties already I discussed. Now properties of different types of solid. You can see non-conductor, molecular solid; conducting, metallic solid; non-conducting solid; conducting liquids; ionic, usually non-conducting, covalent network. Now crystal lattice. What is crystal lattice? A crystal lattice is the geometry arrangement of lattice point in a crystal. A unit cell is the smallest box-like unit form which you can construct a crystal by stacking the unit in 3 dimensions. There are 7 basic shapes possible for unit cell, which give rise to 7 crystal systems used to classify crystals. You can see the crystal structure and crystal lattice of the copper. These are the 7 crystal systems: cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, triclinic. These are the system. So my friends, from here I will discuss in our next video. If you like this video, then subscribe my channel, and thanks for watching.